Good afternoon, everyone. Thanks for giving me some time to present some of the initial research that we've done on the impacts of the Internet of Things in agriculture at the University of Manitoba. My name is Hawley. I'd like to give special thanks to Gary and Dr. Pollowell for their help with this research. So some of my main objectives here are to describe to you some of the projects I've been involved in this area, as well as to illustrate the potential impacts to the market. To do that, I'm first going to try to convince you why food system sustainability needs the Internet of Things. And I'm going to do that with illustrating the course content of our Innovations in Agriculture course that featured last winter, some of the outstanding student experience projects that were funded this summer, and the development of a new student team at the university. So in my mind, from an engineering perspective, the problem of food system sustainability is one of minimizing the amount of inputs that we place in the field and still returning a high yield. And this same philosophy fits well with precision agriculture, which aims to conserve water, reduce pesticides, help support the personnel costs or minimize electricity. But the problem that we found is that precision agriculture is not being well adopted in the Western provinces, and that's because of a lack of professionals, the cost of the technology, and the current cellular and internet network. Now, Bell MTS must have also realized some of these limitations because they helped fund the development of the Internet of Things in agriculture at this university. So what is the Internet of Things? So it is embedded computers in machines, in tablets, in drones that help communicate between producers and the items that they store. They have the potential of giving farmers the ability to understand that in-field variability, to reduce the cost of precision ag, and to give them more bargaining power with the products that they have. So with that said, let's talk about some of these projects. So in Agri 3030, we had this idea of building small localized sensor stations and deploying them out in the field. So we ended up building 10 of these stations and using a drone to communicate the data that they were gathering. So here's a picture of our little prototype. It has a temperature, humidity, soil moisture, and rain detection sensor. So we had to do two tests. One was a calibration test of the sensors, and the other one was a communication test with the drone. The communication test worked flawlessly. We had it out in the point, we had all our stations running, and the drone just picked up information as much as we wanted. Unfortunately, what I found through the calibration test is that some of these sensors were not really designed for agricultural purposes and had low performance, so I would recommend changing these products. Furthermore, if we really want to introduce this system as a potential supplement to changing the irrigation schemes out in a farmer's field, we really need to test the algorithms that are being used in these sensors. The next product I worked with was in conjunction with a company, GrainViz, who developed a 3D modeling technique for grain storage. This allows them to have early precondition determination, infestation detection, as well as different infections in the crop. They do this by measuring the permittivity of grains. And this is very similar to the project that I've helped work on. So here is a test cell that's based off of the United States Department of Agriculture's master test cell to measure the permittivity of products at a certain frequency. So what you do is you place your grain sample into the loading chamber, and then you introduce an electromagnetic wave. The resistance to the formation of that wave is measured as permittivity. You then use that value along with some algorithms to design, let's say, a moisture sensor. So you can see from the preliminary results that this sensor agrees very well with the oven moisture content method. So this technology, a similar technology, has already been developed for the grain bin imaging, and so this is helping towards new product lines that will eventually lead to changes in how we measure moisture. The last project I want to talk to you about is the formation of the University of Manitoba's agricultural robotics team. So I'm coming from the perspective that with the increasing acres farmed per farmer and the increased costs that we need to do for blanket applications of fertilizers or pesticides, that we need to have better control of these systems. So designing automated machines which can earlier detect signs of infection or pests and then precisely apply these fertilizers is an alternative solution to some of these transgenic modifications that I've seen. So instead of eliminating the use of pesticides or fertilizers, we want to reduce it by only selectively applying it to where we need it. Now, this challenge has been funded by some researchers in Rockville, Indiana, who open up a grand prize of $100,000 a year for students competing in these projects. And since we're engineering students, my team and I have been impatient, and we started building a prototype. In the fall, we're looking for other agriculture and engineering students to join us so we can make these systems even better. So if you want to be involved, come talk to me later today. But before we end, let's talk a little bit about this prototype. So here is a picture, if you can see a very small robot in my 10 by 5 meter garden at home, right before any germination has occurred. And it uses various sensors to autonomously navigate this field. And it has an embedded camera which transmits information on the crops back to my laptop. So I'm in the process of designing various HAR cascades which allow us to classify different weed or crop species so that I can begin to further refine those models into, let's say, disease detection parameters and really monitor the health of these crops. So with that, I'd like to conclude and say that the Bell MTS funding has helped address some of those earlier concerns about the adoption of precision agriculture. Because students who are going to graduate from agriculture diploma, degree, and from biosystems engineering are now going to be equipped with the technology expertise to handle some of these new innovations. And these impacts will then spread to the farming community in grain storage, water management, and in the development of new machinery. So I'd like to thank all the people who have helped me with this product, and if anyone has any questions, feel free. Thank you very much.